Well, welcome back, you guys. Your favorite Calculus 2 course. So, previous section, we determined the convergence and divergence by calculating the limit of the sequence of partial sums, right? But this can be difficult, impossible at times. That's why we have some tests that allow us to determine convergence or divergence for different types of series. So, two of these we'll look at today will be the divergence test and the integral test, and as well as I should have wrote the p-series test as well. Okay, so just like last time we mentioned, if we know it converges, then the limit of the nth term will be 0. That does not tell us that is not true. The biconditional is not always true, right? But that leads us to the contrapositive, which is the nth term test, which says, hey, if it diverges, or I like to say it as if the limit does not exist, is not 0, right? Then the series diverges. Right, this is how I think about it. That's the contrapositive of that up above. So let's go ahead and use the nth term test for divergence here on each of these. To start out, looks like we've got the series n squared, n equaling 1 to infinity. Let's go ahead and see what our limit is. And notice we get infinity is not 0. Therefore, by the nth term test of divergence, since the limit n goes to infinity of this is not 0, then the series that we're given diverges. So it diverges. Again, the limit's not 0. Let's do another one here, the second one. Limit as n goes to infinity, n plus 1 over n. Let's do this one algebraically. Let's divide everything by that denominator there, highest term of the denominator. And so we'll have limit n goes to infinity of 1 plus 1 over n all over 1. As we run this to infinity, this will go to 0. I got 1 over this huge number, right? That goes to 0. So I'm left with 1 plus 0 over 1. So I'm just left with 1. Well, the question is the limit not equal to 0? Sure enough, it's not equal to 0. So by the nth term test, therefore, the series diverges. All right, since the limit as n goes to infinity is not 0. About this one, let's test this one. We run this and we get 0. Well, it is 0, right? Again, it is the nth term test says if it's not equal to 0, then we can conclude it diverges. Well, it is equal to 0, so we can draw no conclusions. The nth term test just does not help us. Therefore, the nth term test does not apply, and we can draw no conclusions about the convergence or divergence of the series. Note this is a p-series, and we will address this later. This is anything in the form 1 over n to the p is a p-series, so we'll talk about that later. All right, how about this next one here? We've got limit n goes to infinity of -1 n plus 1. So notice this will just alternate between -1 and 1. based on the value of n, right? This is an alternating series. So the limit is definitely not 0, right? This alternates, so the limit is not 0. Well, as long as the limit's not 0, we can conclude it diverges. All right, how about our last one here? Limit as n goes to infinity, negative n over 2n plus 5. This is a good one if you want to pause it and do a little u-try on this. That'd be great. So if you did this algebraically, you divide everybody by that n from that 2n plus 5 on the bottom there. You divide everybody by n. Let's do this with L'Hopital's, though. Notice I got, if I plug infinity in, I get the negative infinity over the infinity, right? So this is indeterminate in form. So using L'Hopital's this time, take the derivative of the top, derivative of negative n is negative 1, derivative of the bottom is 2 plus 0. So we got negative a half. Well, that's not 0. So once you get your limit of being negative a half, either algebraically or with L'Hopital's rule, then you can conclude this diverges by the nth term test divergence, right? Not a bad time, you guys, to pause the video and go ahead and do these as well as you try out problems. Let's go ahead and use the nth term test here. We got 5, 6 to the n. And if you notice this, I don't know if you want to think about with a table or how you want to think about this. You know, if you did make a table, plug in 1, maybe plug in 5, 10, 100, 5, 6 to the 1, power would be 5, 6, or 0.83. Plug 5 in, right? 5, 6 to the 5th. And I just punched that in with my calculator. I've got it notated here, 0.402. Plug in 5, 6 to the 10 power, 0.1615. We're just trying to get a feel for this. 5, 6 to the 100th power, 1.207 times 10 to the negative 8, right? So this is 0.000001207. Did I say that right? Anyways, bunch of zeros there before the 1207. If I plunge in 1,000, now it's 6.588 times 10 to the negative 80, right? So that thing's got, you know what, 79 zeros, right, before the 6588. So you can conclude, oh, this does, as n gets larger, as n shoots to infinity, does go to 0. Does go to 0, right? And that's because, so as n goes to infinity, the values get smaller, as you can see from the table. And why is that? Well, because 5, 6 is less than 1, right? As 5, 6 is less than 1. So if we'd have thought about this from last test, I know we're supposed to be using the divergence test. So let's conclude with that divergence test before we talk about what type of series this is. Well, since it equals 0, nth term test does not apply. Note, however, this is a geometric series. Right? This is a geometric series with r being 5, 6, right? It's 5, 6. The first term is 5, 6. Next term is 5, 6 squared. Next term is 5, 6 to the third, right? R is being 5, 6. Well, if that is less than 1, it converges. and the sum would be 5, 6 is the first term over 1 minus 5, 6. And so the sum actually ends up being 5. Just a note on that, right? But we're using the nth term test on each of these. Let's do another one here. Let's run the nth term test on this 7/4 to the n. See that 7/4, that's going to be getting bigger, right? If I plug in n, if I do that with the table of values, this is just shooting to infinity. So it's not 0, so we can conclude by the nth term test divergence, the series diverges because the limit's not 0. Note again, this is a geometric series again. Our r is 7/4, and since that is greater than or equal to 1, we know by the geometric series it diverges as well. Again, this question's asking us to use the nth term test to make some conclusions, but I just want to point that out. The geometric series did apply to both of these first two. All right, let's do another one here. We got 3 to the n over 7x squared minus 5. If you take a look at the limit as n goes to infinity of this, notice we have infinity over infinity. So we're going to use L'Hopital's rule. So we got natural log of 3 to the n. There's the derivative at the top. There's the derivative of the bottom. Notice I'm still infinity over infinity, so I got to use L'Hopital's rule again. So I already have a natural log of 3. Now I'm taking the derivative of that 3 to the n, which is another ln of 3 to the n. Take the derivative of 14n, which is 14. Now I run it to infinity. See how I got infinity over 14. So we end up with infinity on this thing, which is it 0? No, it's not. As long as it's not 0, we can conclude diverges. Yeah. This next test is called the integral test, okay, and it's got some conditions. So note the conditions to the integral test. If your sequence is positive, continuous, and decreasing, then the series and its accompanying, if I let f of x be a sub n, if you will, right, then its integral from 1 to infinity, right, this one's with natural numbers here, right, 1, 2, 3, 4. This is with real numbers. Well, guess what? They'll both, as long as it's positive, continuous, and decreasing, they'll either both converge or both diverge. And so you can use the integral to test it. You can use the integral to test it. So number one, what we'll do first is we'll see if it meets the conditions for this first one. So number one, if I think about f of x being x over x squared plus 1. Is it positive, right? If I start with 1 over 1 squared plus 1 over 2, yes, positive. Is it continuous? Are there no breaks in the domain from 1 on? Yeah, there's no breaks in the domain. So positive is positive from 1 to infinity. continuous? And is it decreasing? Well, if you're not sure if this thing is decreasing, again, you could write out the terms and verify that it's decreasing. But let's go ahead and use a little calculus to see if it's decreasing. If I take the derivative, remember the first derivative test, will tell us if a function is increasing or decreasing. So this is back from your Calc 1. Well, this is a quotient. So derivative of the top times the bottom minus the top, derivative of the bottom, all over bottom squared. And so we've got x squared plus 1 minus 2x squared. So I got a negative x squared plus 1 over x squared plus 1 quantity squared. So when I do my first derivative test, I take my points where this thing is undefined. So I take, what are my zeros? And so I got x squared equals 1, so plus or minus 1. Now I don't really care about this because I'm really from 1 on. So I'm not even going to worry about testing around that negative 1. I'm just going to test around the 1. The denominator, x squared plus 1 equals 0. If I set that equal to 0, x squared plus 1 equals 0, those are just imaginary numbers. So there's no critical points for my denominator here. So let's just test around 1. Let's go ahead and plug in like 0. I'm going to plug it into my derivative here, f prime, right? If I throw in 0, I get a positive value. So the original function's increasing up until 1. Then I throw in something to the right of 1, like maybe 2. So I got negative 2 squared plus 1 over 2 squared plus 1 quantity squared. All right, so negative 4 plus 1, I got negative 3 over 5 squared. So that's a negative. So the function decreases after 1. So it was positive, it was continuous, and we've just determined that after 1 it is also decreasing. So it meets the conditions of the integral test. So now the conditions are met. We'll apply the integral test now. Conditions met, we'll use the integral test. So we'll go from 1 to infinity of x over x squared plus 1 dx. And so that'll be, this is an improper integral. So we need a 2x, I'll put it 1/2 right there. And so we've got limit b goes to infinity of 1/2, and then we've got 1 over u. Du. So 1/2 natural log of u, which is the u is x squared plus 1, from 1 to b. So that limit b goes to infinity, 1/2 natural log b squared plus 1 minus 1/2 natural log of 1 squared plus 1, which is 2. 1/2 ln of 2. Well, if I plug in the infinity here, that's going to go to infinity. So we got infinity minus 1/2 ln of 2. So this just ends up going to infinity. So it went to infinity, right? So it diverges, right? So by the integral test, that must mean the original series also diverges. So since the integral diverges, that means the series must also diverge. Let's use the integral test again on this one. Can we apply? Does the integral test apply? Well, note that f of x equals 1 over x squared plus 1 is positive, right? I'm thinking of values if I plug in 1, plug in 2, plug in 3, and so on. It's always positive. It is continuous. There's no breaks from 1 to infinity. And notice it is decreasing as well. Values will decrease for x being greater than or equal to 1. So conditions are met. We can apply the integral 1 to infinity of the function 1 over x squared plus 1 dx. So this will be our u. That's our u squared. That'll be our a. So a is 1 squared, right? And so this will end up being limit as b goes to infinity of 1 over a arctangent of u over a from 1 to b. So we've got the limit as b goes to infinity, arctangent of b minus the arctangent of 1. I run this to infinity. Remember, here's your arctangent. Remember, it's got a horizontal asymptote at pi halves and negative pi halves, right? So as you run that to infinity, you're approaching the horizontal asymptote. So this is going to pi halves minus arctangent of 1 So that means the tangent of theta is 1. I'm looking between negative pi halves and pi halves, so I know that that's got to be a pi fourths. So we got pi halves minus pi fourths, which is pi fourths. Therefore, converges. So by the integral test, this series converges. It does converge. I would note here, even though the improper integral converges to pi fourths, this does not imply that the infinite series it was, what was it, 1 over n squared plus 1, right? Because this would be 1/2 plus, if n is 2, 1/5 plus da da da, right? That does not, because your n is just your natural numbers, that does not imply that the infinite series converges to pi fourths. Again, think to yourself that the integral is all real numbers. With the series, you've got the natural numbers there. So that's not implying that. Don't make that assumption. All right, here's 1 over n cubed. Let's notice here that this is, whoops, that's n cubed is positive, is continuous, and it is decreasing for greater than or equal to 1. So we can compare the series and the integral to see if they both converge or diverge, right? The integral test will tell us that. Or diverge. So let's run the integral test. 1 to infinity, 1 over x cubed dx looks like when this goes to infinity, this is going to go to 0. And so we end up with 0 plus a half. So we end up with a half. And so 1 to infinity of 1 over x to the third converges. Therefore, by the integral test, the series converges as well. All right, let's look at this next one here. If we got 1 over square root of 2x minus 1. Notice we are positive. Again, you plug in 1, 2, 3, 4, so on. It is decreasing, continuous. It is continuous. All right, the only issue here is if x is equal to a half, that'll be an issue. But from 1 on, from 1 to infinity, you're going to be fine on this as far as continuity. And you are decreasing again. So we can use the integral test to compare. I need a 2 dx, so offset of the 1/2 here. So I got a limit. B goes to infinity, 1/2, integral from 1 to b of 1 over the square root of u du. So that'll be u to the 1/2 all over 1/2, so times 2. Notice those cancel, so we have limit. B goes to infinity of u to the 1/2, or the square root of u. Well, the square root of u, remember u is 2x minus 1. And so we've got limit b goes to infinity, square root of 2b minus 1 minus square root of 2 times 1 minus 1. And so notice this right here, that's going to shoot to infinity minus the square root of 1, which is 1. So we just end up with infinity. So this integral diverges. Therefore, by the integral test, the series also will converge. All right, the last one for today is called the p-series. Now, last time we discussed this harmonic series, right? This harmonic series, and we used a table of values to show that it very, very, very slowly does diverge, but very slowly. But anything of the form 1 over n to the p is referred to as a p-series. And if your p is less than or equal to 1, greater than 0, it'll diverge. Okay, just like this one, the p here is 1, right? So since it's less than or equal to 1, it'll diverge, right? And we showed with the table of values that it diverged, but it was very slowly, right? So anytime your p is less than or equal to 1, greater than 0, it'll diverge. Otherwise, it'll converge if your p is greater than 1. The integral test can establish the convergence or divergence of p-series, but we don't want to bother with the integral test every time, right? But with the, if you notice with the p-series, you'll be continuous, you'll be decreasing, right? and you'll be positive. Positive, continuous decreasing. So it meets the conditions to just use the integral test, but we're not going to bother with it because now we have a p-series. So we'll use the p-series test instead. So here we've got the harmonic series, right? Our p here is 1 over n to the 1 power. So we say, well, since p is less than or equal to 1, by p-series test, we have p being 1. So as long as it's less than or equal to 1 greater than 0, it must diverge. Well, what if p is now 2? 1 over n to the p. P is now 2. Well, by the p-series, we have p is 2. Anytime p is greater than 1, it must converge. You guys, this is a good time. Why don't you guys go ahead and try these two? Good time to pause the video and go ahead and use the p-series on these two. Well, notice your p here is 2/3. There's that one. Series must diverge. So you have p less than or equal to 1. Now this one by the p-series we have p is bigger than 1. So by p-series test, series must converge because we're bigger than 1. Thanks so much for watching. See you guys next time.